Thank you very much for your lecture, and thank you for not blowing up my head, but it was expanding.
You were on the front row. You were writing the firing line as
yes,
well. Yeah,
I know. That's why I covered my ears. Thank you. Anyway, but on the gigafactories that are being built now, what goes actually inside them?
Okay, great question. It's kind of the best kept secret in the battery industry, but I'll tell you what I know. These things are called gigafactories for a reason. They're done at such enormous scale. A gigawatt hour of batteries, as I said, is equivalent to 1 billion of these. But actually, many of these are tens of gigawatt hours in terms of the installed capacity. Nissan and Envision in Sunderland have had a gigawatt hour production facility for more than a decade or thereabouts. They've been making gigawatt hours of batteries to go into Nissan Leafs. And people have just scaled this to become bigger and bigger and bigger. And those images that you can see just show these are literally some of the world's largest buildings that are just churning out batteries. But what do they look like inside? Well, first of all, you've got to synthesize your materials, or you've got to truck them in. If you're synthesizing materials, you've got things like graphite. So this is our sort of stuff, looks very similar to pencil lead, but in such vast quantities you wouldn't imagine. You take the graphite and you take your metal oxide electrode and you mix it up till you make a slurry. So that sort of ink, if you can hear that inky sort of slurry sound, you mix it up in these giant mixers which look almost comically like giant kitchen mixers that stir these things together in order to make an ink that can be printed. Then you've got your newspaper printing press. Your newspaper printing press moves extraordinarily fast, and you print these things onto metal current collectors and roll them up into really big reels. Once you roll them up into really big reels, you roll those reels into small reels, and you put the whole battery together in, for example, this jelly roll configuration. You've got your anode and your cathode stacked and then wound up together and squeezed into a can. So if we were going to look at a real one, it looks something a little bit like that. You've got your anode and your cathode and a plastic separator, all squeezed as tightly as possible into that can. So once you've stuck it into the can, you then fill it up with your liquid electrolyte. You then seal everything with a cap like this one, and then you charge and discharge it for the first time. And you would be amazed at the quantity of batteries that are literally in a factory being charged and discharged for the first time. Gigawatt hours of batteries that are just going through their paces for the first time, being charged and discharged before they get let out the door. And once they get let out the door, obviously they do wonderful things like make bike batteries or vacuum cleaner batteries or electric vehicle batteries. And again, the building blocks for all of those are really rather similar.
Oh, it's fascinating. I was just going to add, I mean, I think that raises an interesting point, which is it a problem for researchers, you know, you're at UCL, a public university, being sponsored by, you know, public money, but there are private companies out there, and how hard is it for you if lots of this research is, like you say, commercially confidential? And, you know, is that a problem in the battery industry now that so many commercial players are coming in and you won't necessarily know? They might have come up with some great bit of technology they're not telling you about.
Well, is it a problem or is it an opportunity? You see, Martin. So there we go. What I would say is if you look at the history of the lithium-ion battery, it's such a wonderful story of collaboration and multidisciplinarity. You've got, with the 3 Nobel Prize winners, 2 people that have worked in industry, and 2, I know there's only 3 in total, but one guy spent some time in industry and some time in university. But you've got that mixture of people from Sony and Exxon and the University of Oxford and the University of, forgive me, Binghamton, is that right? Where Stan Whittingham is? Yes, thank you very much. Wonderful. Somewhere in the US. So you've got this wonderful story of academic industry collaboration that's right at the very birth of the lithium-ion battery. So, yeah, of course it's challenging and everyone's got industrial secrets and no one really knows what's going in everyone's gigafactories. But when it works, that sort of coming together of academia and industry, I think, can be really exciting and very, very impactful.
Excellent. Any more questions? Oh, there's a question at the front.
One's in the front row.
Hi. What do you think the biggest challenges are for gigafactories in the UK in particular?
So, forgive me, what do I think the biggest change is in...
Gigafactories in the UK.
Gigafactories in the UK. Well, I mean, it's great that we will have gigafactories in the UK and people have committed to building them, and that's very exciting. I think that the initial wave of those gigafactories will be heavily focused on lithium-ion batteries to service the automotive sector. But what I hope the biggest change that we'll see in the UK is the early adoption of next generation chemistries, sodium-ion batteries, solid-state batteries, lithium-sulfur batteries. Because whilst there is a great history of lithium-ion battery research in this country, perhaps it's fair to say that the history of the commercialization and industrialization of batteries in this country is perhaps slightly less well established. Although a lot of the fundamental building blocks and the early intellectual property came from UK universities, it was in Japan and Korea and the Far East where a lot of these first gigafactories were established. And so I hope that what we can do here in the UK is we continue to lead the development of a next generation of chemistries, is try and take a lead on the deployment of the manufacturing at scale of solid state, of sodium ion, of lithium sulfur. So who knows what the future will hold, but that's my great hope that we will be the leader on the next generation chemistries.
Fantastic. Actually, there's a question just behind. I'm trying not to make you run around too much, Courtney, so keeping your life easy.
You haven't mentioned the sort of alternative approach that some people are taking. If you've got a storage facility onshore and you're trying to store electricity from your offshore windmills or tidal whatever, you don't need to worry about the weight or the size of the battery. And these people are actually looking, going back to the copper sulfate, copper, and copper zinc systems, and trying to develop the technology that we've been using to electrowind copper for the last 120 years. But then, I mean, it isn't a transport thing, and it doesn't matter what size it is or how much it weighs. But there are people looking at that and saying that may be the way to go.
You're right, and I think that we need energy storage for so many different things, and the lithium-ion battery is something that features very heavily in so many different sectors, but it's not necessarily the right answer for every sector. You can store energy in very creative ways. For example, the iron-air battery, really scalable, is basically a lump of iron that is sitting there rusting, right? That's the electrochemical reaction, it's just rusty iron. If you can somehow harness that at huge scale and make it sufficiently cheap, then I entirely agree. There are no shortage of exciting options. And we come back to that standard reduction potential series list. We can cherry pick the different redox reactions, the reduction and the oxidation reactions, match make them together to make a battery. And one that is cheap and scalable is obviously very attractive for large-scale storage. I also want to just reflect on other things that are not batteries at all. And I was delighted that Charlotte earlier today showed me some correspondence between Michael Faraday and William Grove. And William Grove may be known to some of you in the audience. He was one of the pioneers of fuel cell technology. Of course, when we're looking at Faraday's voltammeter, we said that he was using electricity to split water into hydrogen and oxygen. And he was measuring the volume of hydrogen in order to quantify the amount of electricity. But that's exactly what we can do at scale in order to do energy storage here in the UK as well. I think we're not just going to be looking at just lithium-ion batteries. We need to look at a broad portfolio of things, whether that's large iron-air batteries or aluminium production or the production of hydrogen using an electrochemical process. And this, I am so nervous about holding this, especially in front of all these chemicals. This is a letter that William Grove wrote to Michael Faraday, and it was in 1842, describing the fuel cell principle. And when we've got a hydrogen fuel cell, we can either create electricity, convert electricity from the chemical reaction of hydrogen and oxygen, or we can put electricity in and we can generate hydrogen that might act as a large-scale energy storage device. And this is one of the first descriptions that Grove, in this beautiful sketch in the letter to Faraday, made about the fuel cell principle. So I think that sometimes you read in the popular press that there'll be a battle between hydrogen fuel cells and lithium-ion batteries for electric vehicles. But we need to get past that. These guys, William Grove and Michael Faraday, back in 1842, recognised the intersection and the benefits of both technologies, and we really need to come back to that. It's not a competition for one technology to win. It's really about having a portfolio of options, whether that's entirely different batteries, whether that is using hydrogen, whether that's using fuel cells. I think we're in the age of electrochemistry, and bringing all of those things together in order to be able to try and meet net zero targets is something that motivates me enormously. So I will just read some of this letter from William Grove to Michael Faraday. My dear sir, I've just completed a curious voltaic pile which I think you would like to see. It's composed of alternative tubes of oxygen and hydrogen, through each of which passes a platinum foil so as to dip into separate vessels of water acidulated with sulfuric acid, and the liquid just touching the extremities of the foil, as in the rough figure below. And this remarkable letter illustrates that fuel cell concept so articulately and for the first time back in 1842. And as I said, I think that we need to not encourage a competition between these technologies, but understand the synergies that each of them can offer. I will pass that back to you, Charlotte. Thank you very much.
I think I'm going to use the word acidulate the next time I have fish and chips. I'm going to acidulate my chips with some vinegar. Are there any more questions there? Thank you.
What's the environmental impact of all the lithium that's going to be needed for these massive battery production?
I think that's a wonderful question, because we are doing this with noble goals to achieve net zero, but actually if there's so much embedded carbon within the manufacturing and the supply chain, then when do we get our payback? I think that certainly we need to have batteries that are operating for a long time and as durable as possible and in the right application in order to make that sort of net saving in terms of our carbon emissions with the current generation of technology. Don't get me wrong, buying an electric vehicle is great for urban air quality and has noble benefits in terms of the current improvements that you can make versus a combustion vehicle in terms of greenhouse gases. However, we can do better, because you rightly point out that these materials, like the lithium cobalt oxide materials we talked about as a cathode, they're dug up from the ground. And we need to really get to grips with the sustainability of that process. Now, that could be improvements to the mining process itself. That could be shifting gears to look at different materials. But it could also be thinking about a circular economy for the batteries that we already have. I briefly mentioned at the start, one of the goals of the Faraday Institution was to improve the recyclability of batteries. Because let's face it, when you finish with your mobile phone, it probably just sits in your sock drawer and you don't do anything with it. But when you finish with your electric vehicle battery, you've got probably 7,000 of batteries not dissimilar to this. You've got about 1,100 in this one, about 7,000 of these guys if you buy a Tesla. That is a huge recycling challenge. And that's driven both by sustainability and by economic concerns. People want to recover value from this investment. But that also inspires this idea of a circular economy. Once we have a sort of finite amount of material to deal with, it should be absolutely our responsibility to recycle, recover, and reuse these materials. So we're not always going back to a mine to dig up more cobalt. People talk about surface mining. They're taking things from the rubbish tip and they're extracting the valuable minerals and elements like cobalt from our battery waste. And I think that's something that we should absolutely encourage. And the Faraday Institution Relib project is totally leading the charge in terms of battery sustainability and recycling. But it's something that we always need to improve. Sorry, yeah. So forgive me, I don't know if you call that.
The recycling process might also have its own problems in terms of, it takes energy and,
Of course, you're absolutely right, yeah. And I don't think that at the moment there is a single recycling technology demonstrated at scale that will cope with this enormous influx of batteries that we expect to come from, the electric vehicles that will come off the roads over the course of the next decade. So absolutely a research challenge. And naturally, with the noble ambition of reducing the carbon footprint of the overall battery life cycle, we need to be conscious of the carbon footprint of the recycling process itself.
Any more questions for Paul? Anyone on that side? Or someone? I'm going to make you over there. Thanks. And I'll get to the person over there later as well.
What is the benefit of using multiple small cells over a larger cell? And is there a physical limit on the size that a cell can be?
That's a good question, and different manufacturers have different approaches. I think that if you cast your mind back to about 2008, Tesla were really the only people looking at the use of cylindrical cells in vehicles. And the reason that they started looking at literally cells like this guy, this is an 18650, which is 18 millimeters across and 65 millimeters high. The reason that they started looking at this for the early models of the Tesla Roadster was because that's what was available at scale and sufficiently cheap. Because these batteries were developed to go into old-style laptop batteries, the ones that used to click onto the back of a laptop, probably contained about 6 of these guys. And so Tesla were really just leveraging the economies of scale of that very well-established industry to buy these as cheaply as possible, stack them all together, 7,000, and you've got an automotive battery pack. But as well as that, you have quite a good fault tolerance as well, because within 7,000 batteries, it doesn't really matter if one breaks. If you've got 300 batteries and one breaks, you're perhaps slightly more in trouble compared to the sort of fault tolerances that you can engineer in that. However, other battery manufacturers and vehicle manufacturers use much larger cells, like the ones that you can see here. And you probably need about 400 of these cells in order to make an electric vehicle battery pack, compared to about 7,000 of these guys. And I think the jury's still out. Some manufacturers are going for pouch cells, some are going for prismatic cells, some are sticking with the cylindrical cell format. We've seen recently that Tesla have announced that their new batteries will be larger cylinders, so certainly they're trying to reduce the cost and improve the energy density by scaling this up somewhat. But it's sort of horses for courses at the moment. Some manufacturers are going with pouch, some with prismatic, and some are sticking with cylindrical.
Excellent. Actually, do you want to take the question from the middle of the row, and then I'll come over to people on this side.
This may be a little bit unpolite questions, if you please forgive me. So once my friend asked me about the question that he's also doing the research in batteries, and he says, how many time do we left before the nuclear fission reactor that is under controlled ones getting mature? So basically we get like unlimited power supplies. And maybe if this technology is combined with like wireless charging, or somehow maybe the batteries become not as important as for now. What do you think about that?
Okay, so there's a few questions in there. I think the first one was, will we still need batteries if we've got nuclear fusion?
Yes, and particularly if you combine it with wireless charging, then presumably you could just zap power anywhere you want, and therefore we don't need batteries at all.
Right,
Quite a provocative question to ask at Battery Talk, but we'll go with it.
I mean, I think that we will always be in a position, even with wireless charging, where you're still going to need a battery, right? Even to wirelessly charge a vehicle from nuclear fusion, the vehicle still has to have a battery inside it. In terms of where we are with nuclear fusion itself, of course, what a wonderful technology if we can get that to work. But it's not going to come along in time to meet our net zero targets. So I am very excited by the blue skies research that's being done in terms of nuclear fusion. I think there were some really exciting results actually from the US Fusion Lab just a few weeks ago, when they've managed to sort of recover about 70% of the input energy from a nuclear fusion experiment in terms of the amount of energy that was generated. But at the moment, it's still very much a low technology readiness level, blue sky sort of technology. But we need net zero much sooner than that. We've got to get to decarbonisation by 2050. And so we can't rely just yet, unfortunately, on nuclear fusion.
Oh, there's a question along that row as well. I might as well go for it.
Hi, thank you so much for your talk. It's really brilliant. I was just wondering, do you think we'll ever be in a position to 3D print batteries? And if so, how soon?
So do I think we're in a position to
3D print batteries?
3D print, but I briefly mentioned 3D printing actually, because the Faraday Institution Nextrode program is looking at advanced manufacturing, and one of the sort of speculative technologies that we might use is 3D printing. I mentioned that when we make electrodes like these guys that you can see down here, we use a newspaper printing press. So that's kind of a quick and dirty deposition technology. 3D printing, of course, is all the way at the other end of the scale. We can get phenomenal control of the materials and the morphology of those materials. We can make brilliant batteries, but they're so expensive. They're so expensive because it takes so long to 3D print the materials that would go into a battery of this kind of size. And so I think what 3D printing offers is a really exciting route, but at the moment, unfortunately, it's just not technologically mature enough to be cost competitive. But in the university research lab, Absolutely. We are 3D printing batteries as we speak, because only by doing that can we demonstrate how good a battery could be, but also improve those 3D printing technologies so they can become cost competitive with the current generation of printing. So it's a great question, and we're really excited by 3D printing. It's just too expensive at the moment.
Excellent. There's a question. There was a gentleman over here who had his hand up earlier. I don't know if I want to... go on, I'll go and grab the mic for you.
Thank you. I've heard about like graphene as a kind of miracle material that's going to like charge your mobile phone in 3 seconds and last 6 years and stuff like that. Is that just hype, or is that a feasible thing?
3 seconds, that is definitely hype, yeah. But in terms of fast charging, I mean, we are definitely getting better. I mean, you can look at that in the products that you can buy nowadays, right? You can get batteries which will do 80% of an electric vehicle charged in 45 minutes. That's hugely impressive compared to where we were even 10 years ago. There are a range of challenges that have been overcome in order to even to implement that technology. So you've not just got the fundamental materials challenge, engineering materials, often nanomaterials that can accept and deliver that power quickly enough, but also engineering the overall electrical system to be able to handle those extreme currents. I talked about the Rimac hypercar. When you discharge that at its highest power, it generates 1.3 megawatts of power. So that is an absolutely enormous amount of current flowing through your battery. So just the engineering challenges of dealing with the heat from that current are extreme. But we've made great progress, and I think we will continue to make good progress. Some chemistries offer a sort of holy grail for fast charging, particularly ones where there's maybe some capacitive behavior. I've not really talked about capacitors this evening, but things like the Leyden jar were those first electrical capacitors. One of the great things about capacitors is they don't store a lot of energy, but they can deliver and accept it really quickly. And so perhaps intelligently hybridizing batteries and capacitors is one route to being able to do really fast charging. But I think we need to ask ourselves as well, how fast is fast enough? Because if you're always, going to get a coffee while you're charging up your car, maybe 15 minutes is fast enough anyway. And I think that the sort of roadmap in terms of battery developments will take us to sort of half an hour or less in terms of the sort of typical charging times. And certainly from my perspective, I think, go out for dinner, charge up the car, come back to a fully charged battery seems like a pretty good deal.
I think also specifically the question was about graphene and...
graphene, sorry, I missed that, forgive me.
I was just going to say, if anyone has any communications from the University of Manchester ever, they will not shut up about how amazing graphene is and how it's wonderful and how it was made, by Andre Geim at the University of Manchester. But for the rest of us, I sort of feel like, has its potential been oversold? Has it been hyped too much? Or?
I'm not sure that I'm qualified to answer that, but let's talk about how we can use it in electrochemical devices. Graphene has wonderful electrical properties. It can also do some capacitive and Faradaic charge storage. It's also extremely strong, but it's still pretty expensive. When we think about the graphite electrodes, some people joke and they say, graphite, that's just my multi-layer graphene, okay? So I've just got all this graphene stacked together. I can sell you multi-layer graphene. It will cost you a fortune, but really it's just pencil lead. But yes, in short, do I think that there is a role for graphene in electrochemical devices? Absolutely, because it's got the electrical conductivity, it's got a contribution to the Faraday reactions, it's got the strength. If we can make it cheap enough and scalable enough, I think we will increasingly see some magic graphene fairy dust getting sprinkled into our batteries.
Fantastic. We've got about a couple of minutes left, so I'll just take... you've asked a question before, so if anyone else hasn't asked a question, I'll pick them preferentially. Oh, Courtney, there's a person right at the back there.
Do you think that we will meet or exceed the government targets on shifting away from petrochemical transportation to electricity?
So do I think we're going to beat the targets in shifting away from combustion vehicles?
Yes, indeed.
So I'm going to look to Matt Howard in the audience. Is it 2030, Matt, when we've got to stop the sale of combustion vehicles? Yes, with an asterisk. Okay, so let's say we're aiming for stopping sales of combustion vehicles to consumers by 2030. That's pretty ambitious, right? We've only got 9 years, just about 8 years and a bit to go in order to achieve that. But ask yourself, in 8 years' time, do you think you'll be buying a petrol vehicle or an electric vehicle? Because I think I'm going to be buying an electric vehicle because I see these sort of crummy old petrol vehicles driving around, stinky, fumey, they're not sexy high-tech like the electric vehicles that we get. on the streets nowadays. So I think that electric vehicles need to be made cheaper, but I think in terms of a consumer choice, the pendulum has already begun to swing towards people wanting electric vehicles, not just because of green credentials, but also because of performance, also because of some of the tech that's integrated into those vehicles has become so attractive to consumers. So I can't afford to buy a Rimac yet, but I hope I can buy a Volkswagen e-Golf, and I think that a lot of consumers will be naturally shifting towards that mindset anyway. So with 2030 in mind, are we going to achieve the government targets? I hope so. I'm optimistic. I certainly think that from my perspective, by 2030, I will be driving an electric vehicle. I should note that unfortunately at the moment, I still drive a combustion vehicle. Electric vehicles are expensive and they're difficult if you haven't got off-street parking to charge. But of course, those are the things that we're tackling when we look at those Faraday Institution targets. We want cheaper batteries. We want ones that can charge more quickly. And I'm really optimistic that we can get there and we can make electric vehicles a sort of mass market possibility by 2030. So I really hope so, and I'm optimistic, I think is the short answer.
And has anyone got a final question for Paul? Oh, no, there's one person there who hasn't asked a question, so we'll go for him. But you can speak to Paul at the end. I'm sure...
I will have happy to stick around at the end,
please
of course.
do. Obviously, Charlotte will be guarding these very precious, priceless objects from the history of science with her life. But do come and take a close look, because it is kind of amazing to get a close-up look at Faraday's notebooks and the Voltaire.
Thanks, Paul. You sort of talk about fuel cell during your speech. So I was wondering if you are aware that there are actually hydrogen combustion engine being developed. So I'm not sure, do you have a comment whether this is more readily applied than fuel cell in the near future?
So forgive me, Martin.
So that was a question about fuel cells and saying also there are hydrogen combustion engines out there as well.
Okay,
and could you see maybe a hydrogen combustion engine and a fuel cell maybe being combined to get the sort of benefits
Excellent.
of both
And forgive me, I've got really bad hearing, and with lots of masks and bright lights, I'm sorry that I'm asking Martin to sort of repeat the questions. But so do I see a role for fuel cells and for hydrogen combustion and for batteries? I mean, I'm a technophile, so I say yes to everything. I would say that the hydrogen combustion concept kind of dropped off the radar for quite a long time. If you look back to the late 90s and early 2000s, BMW were really pushing hydrogen combustion, and it pretty much dropped off the radar for the 2010s. However, it seems to be undergoing a bit of a renaissance at the moment, and I think that net zero targets are ambitious. Electrification of the transport sector and decarbonisation of the transport sector is difficult. And so we're going to need all these technologies. And I don't think we should be ruling anything out, whether that's nuclear fusion, whether that's hydrogen combustion, whether that's large-scale metal air batteries. You know, I think the future will be greatly strengthened if we have a diverse portfolio of energy storage and conversion options. But I do think that electrochemistry is at the heart of so much of that, because even if we are ultimately using hydrogen as part of a combustion engine, it may well have been produced via a hydrogen electrolyzer, such as the one that we're seeing here, based on, of course, the wonderful discoveries of Michael Faraday and William Grove. So I am not taking anything off the table, but I think electrochemistry will have a role to play in all of those future scenarios.
And I think that's a very good point to end on. So it just remains for me to thank the Faraday Institution and to thank Paul for a fantastic talk. Thank you so much.
Thank you. Thank you.